Good morning. I would like to introduce you to our new webinar where we show the latest paper we present at European Turbomachining Conference in Hanover. It is a collaboration between Imperial College London and ToffeeX. My name is Francesco Montomoli, and I would like to acknowledge my co-authors Thomas Ries, Stefano Forino, and Ruben Tomlin for this work we are going to discuss today. So, what is about? It's about fluid topology optimization for fin cooling, where we do what is called a design exploration of different solutions. So, we show what you can achieve today using fluid topology optimization in this kind of coolant technology. Cooling. Why this is important? Because it's important to increase the efficiency and reliability of gas turbine. The turbine entry temperatures, so the gas temperature in gas turbine is about 2200 Kelvin, is very hot. And a variation of 30 degrees on the metal surface can change the life by 50%. So this is the reason why we need a more and more complex coolant system. In the center here, you see a classical rotor blades. On the right, you see our vision about 10 years ago, where we say, okay, we want to achieve this kind of organic bio-inspired shapes that can have a better coolant performance. At the end of the day, what we do, we want to do a kind of adding vanes to proper gas turbines, similar to what you have in your arm today. So, and with additive manufacturing, EDM, and other advanced manufacturing technology, it's possible to have a new complex geometries. Okay, so with ToffeeX, we build a lot of very cool geometries, and it's possible to be almost any possible geometry. Of course, there are manufacturing constraints, but we show this is possible for heat sink, for example, for cool electronics, heat exchanger. This was presented at IGTI 2024. Cold plates for different aeronautical electronics application was presented at Euroturbo 2023. The conformal cooling, manifolds, fuel cells, flow mix, and carbon capture that has been presented in different occasions. So look at the geometry. The first question that I'm expecting from you will be, okay, Francesco, are these results manufactured? Are just pretty pictures, are verified, and so on? The answer is yes. This geometry has been manufactured and independently verified by different companies, considering that the paper was presented in Germany. So I will use exactly the same example I used during the presentation. So in this case was a geometry that was designed using ToffeeX solver and has been manufactured using Constellium material by Fraunhofer and has been also independently verified in terms of performance. It's a mix of convection, forced convection, and natural convection. If you want more details, please ask Nicola Casari at ToffeeX. He's more than happy to explain what it's about, why it looks so crazy, and what is the geometry. So one of the questions that we were asking ourselves, can we apply to fin cooling? Yeah, because the fin cooling is not really a wall-bounded flow. It is a wall-bounded flow, but it's a bit more complex, multiple flows that are mixed. And also we were asking because nobody did before in literature. So we say this is pretty cool case. It's something we want to explore and to see if this is possible. Why do we care about fin cooling? We care about fin cooling because it's very powerful, because it creates a shield around the blade. This one is a rotor blade. Around, as I mentioned before, there is the gas coming 2200 Kelvin. Most of people don't know what it's about, but to give you a little bit of context, it's about half of the temperature of the sun, okay? So what it does, it generates a cold air outside and protect the blade. And this blade that is thick just a few millimeters is holding the weight of about 100 mini cars, okay? So the forces we are discussing about are very high, higher than common experience for people. So this is the reason why it is important fin cooling, because it's protecting this tiny element from falling off or it change the life of these small parts. That is very important for the turbine. Fin cooling development is not new. Okay, several shape geometry have been proposed in literature. You can find a lot of elementary, fundamental studies starting in 50s from Shapiro, Eckert, et al. And after we say there are several studies that I didn't mention here. Okay, so but let's say a good contribution to this kind of geometry was given by Gosling when in around the 70s he understood that the main mechanism of field cooling is driven by the lift-off that is generated by the redistribution of the boundary layer inside field cooling. Okay, when field cooling is coming out, you can show that the main like a surface cover is driven by the intensity of this Kidron vortex. They have exactly the same mechanism of gas turbine of the passage vortex. And if you change the shape of the coolant, you can control these vortices and then to have a better or worse surface coverage. Okay, this was like a study by many different people. In particular, like even if I didn't mention here, there is an important work done by Sidenstick and also like from all the Karlsruhe studies done on this kind of geometries. Okay, the ETS like has been a forefront of this design for many, many years. And like you can see that after about 20, like in 2010, more or less, using computational fluid dynamics and like a more, like a freeform CAD geometries, you can obtain like this kind of strange geometry here that has been patented by MHI that I developed like when I was like at University of Cambridge. The basic idea is that if you add strange shapes, like if you want the steps in front of the coolant, double back facing step is called the geometry. The coolant, this kind of pink this slime coming out from the blade, can have like a better distribution. When it's better distributed, it has a better coverage like on the gas turbine. And this is good. This is something we want. So, but this has been done mainly by experience and first principle. What we want to see today is about if this can be done using topology optimization. So first of all, what is topology optimization? It's not a method, so sorry for the name. And like I copied this picture from online, it is at the reference. And long story short, like it refers to the capability to move across topology. First of all, what is a topology? A topology, like there is a very beautiful mathematical definition. I'm not a mathematician. So, but what it's about is telling you that you can morph, for example, a mug into a donut. Okay, if you look for this video, it will be very clear, not from us, like it's something I found online, how you can morph like step by step from a mug into a donut. So in theory, like these two, they have the same geometries, but it's not possible to morph a donut in a sphere, mainly because there is a hole in the middle, okay, and the hole is breaking the topology. But you can morph the sphere into this kind of strange summary. So long story short, if you're using standard optimization techniques, you will never be able to explore the full design space because like you're bounded by the topology you pick at the beginning. Topology optimization allows you to jump across topologies. So it will tell you that you can move from a mag to a summary and you cannot without just simply morphing your geometry. So it's a big step like in optimization phase. Fluid topology optimization, this is the slide that my people, like people at ToffeeX give me. Long story short, you need to minimize something, for example, the maximum temperature, the thermal gradients and so on, subject to some constraints, okay? So you put everything together, you build what is called the dual problem, and this way you can minimize this functional, and like at the end, you get the optimal. There are several different mathematical techniques to achieve these results. I'm not going to do that. I'm not a mathematician, but just to let you know, like you can find the solution in many, many different ways. Fluid topology optimization, at the end, is more common seen by many people. Like it's based on these kind of things. You define like what is the objective function. So it's a multi-objective optimization where, for example, in this case, you minimize pressure losses and you minimize like the maximum thermal field, like maximum temperature in your geometry. Constraints by what? Constraints by the fluids. We are trying to deal with the fluid dynamics. So you need to be sure that you are the equation you're going to solve with fluid dynamics. And also you consider like the fact that you build like some structure inside, and this is what is driven by what is called permeability, using some turbulence model. And depending on your turbulence model, you have different kind of solution, and you achieve different geometries. Again, as before, there are different techniques to use and to develop and to assess this kind of framework. So I decided to take like a very well-known test case. This one is based on Institut Turmes-Strumong's machine, and I modified a little bit the test case. Why? In the original test case, the coolant was not coming perpendicular from the bottom, but it was what is called in cross flow. There are some beautiful papers from Schulz, Whiting, some Weber, and others that show like this kind of geometry with different conditions and so on. This is just a simple example of what is called a shaped hole, and is very common. So the majority of the gas turbine coolant system you can find today are more or less based on this kind of layout. Okay, so even if you find the different geometries in literature, let's say this is a kind of trivial standard fin cooling shaped hole. And for people who want like a more to see the mesh, the condition and so on, this is like if you want your background mesh, okay? So like we did some assessment, like at the end, like we have an inlet cooler coming from the bottom, viscous wall, inlet hot gas, periodic on the sides, and maybe you wonder why, Francesco, you don't use a symmetry in the center of the coolant hole. The reason is simple, because I want to see like if there is any non-symmetric solution that the code was generating if this was not too expensive, and to be honest, it was not really expensive. So what do we want to optimize? Okay, this is the first time that topology optimization is applied to fin cooling, so this does not help. Okay, if you don't have anybody in literature doing this before, you cannot copy, so this is a problem. So what to do, which condition to apply? Yes, I need to invent them. So first of all, I decide what is the optimization area. So I decide, okay, let's change not only the coolant hole shape, but let's start from already an optimal solution. This is never a good idea in optimization. In optimization, if you start from already an optimal solution, well, it's not going to be massively different. In reality, we say, okay, let's see what is happening. Okay, so we consider the code can modify this kind of yellow area, where like you can optimize like the inside of the channel and a region outside the coolant channel about 0.2 diameter. Why 0.2? This is based on experience, simple as that. Objectives, we decide to use like a maximum heat transfer, cool surface, not plate, and like minimize the pressure losses. Why I want to maximize heat transfer? Well, the reason was this one. I say, okay, if the surface that you want to cool is very hot, and the coolant, as the name is telling you, like it's very cold, so at the end of the day, like you will have the maximum cool surface, but you will have the maximum heat transfer. So like I say, okay, this maybe is a good idea. I will show that maybe it's not one of my best idea ever, but like this is where we start from. And we show like what is a good point of this approximation and why this can be like not your best idea. So, and okay, what we have here, this is on the top right, I have a fake Pareto front. This is just completely made up using PowerPoint. So, but just to explain a little bit where we are, okay? So this is a ideal like a fake Pareto front where you have like eta, is adiabatic effectiveness, how much you are covering your coolant, and the losses on the x-axis, okay? So this multi-objective optimization in this case is not really multi-objective. I kill completely the thermal feed. I say, let's just minimize pressure losses. What your code is building this kind of blue region here, where like is adding material where in this kind of small separation here at the entrance, where the fluid like is separating. This is common to almost all the coolant system that you find in fin cooling. Okay, usually they show a little separation like in this part of the channel. But what is strange is building also some material in what is called the upstream edge of the fin cooling. And this is strange for us because it is not something you expect. But if you think about fluid dynamics, this is the region where you have like the higher the stresses between the fluid that is coming and the ejection. So it makes sense that to minimize pressure losses, it's just adding a little bit of material there to shield this area. After, let's add a little bit of heat transfer. So I increase a little bit of heat transfer. So what is happening? So again, I'm moving the solution in my fake Pareto front on the center, and I will have that is the coolant, like it's building this kind of strange splitters that an ETC was called from a colleague of us, like were called like kind of fences. I really like the name fences, even if the original paper we call splitters for lack of my personal imagination. So what they do, you can see that these splitters at the end they go against the kidney vortex, and so at the end we favorite like the fin cooling like effectiveness. Okay, so you will have exactly the same geometries were developed before, so they minimize the pressure losses, but you have the dome in front of the upstream edge is increased, and you will have like a more and more complex structure downstream that are mainly driven by the fact that you want to minimize hidden vortex. What happens if I increase even further the heat transfer? What we will have something very cool. So we'll have a geometry that, first of all, we have this kind of split that are becoming more and more aggressive. Also, like you have the original coolant hole, not only put a dome in front, but split the fluid like in 3 different coolant holes. And if you cut like the flow field like with 3 planes, you will see this kind of classical like distribution of coolant jet that is like split like in 3, that is similar to what you can use in like a 3 holes structure in like in field cooling. This has been proposed by other people in literature, but it's pretty cool that the code was able to find this solution without any clue about the previous results in literature. If you want a little bit more detail on the geometry, what is happening, the fluid, the hot gas is coming from the left to the right, this kind of white arrow. Easily you have a converging flow in front that is similar to if you want to a back-facing step I was showing at the beginning. The fluid, like the hot gas, hit the central part of the coolant. The coolant is to be shielded by the dome, as I was discussing before, is moving laterally with these arrows, and like is covering this surface as well. At the same time, you have this kind of 3 coolant holes distribution that like is generating a more uniform distribution. And downstream, we have this kind of generation of splitters, if you want, is end-wall contouring that build like a more uniform coolant distribution. The geometry is complex, well, maybe a little bit too complex like for our taste, but it's still very cool to see. In terms of lateral effectiveness, if you put these 3 geometries from the top to the bottom, like on the right, you see more or less what is happening. If you have like just a little bit of like, if you want a pressure losses, you have this kind of green distribution from a blowing ratio 1.2. If you add like a more heat transfer, like you will have that the lateral the effectiveness become very uniform, very flat. Just to remember everyone that this geometry started from an optimal solution. If you ask Francesco how you compare with the baseline, well, the baseline is not very different in terms of effectiveness to what you see in the green line, okay? So like the green line is more or less the optimal, where you minimize a little bit the pressure losses without doing more or less anything to heat transfer. So like this graph will be very similar to what you achieve, also like in case you want to compare to the baseline. But I didn't like too much the geometry, mainly for a reason. Like if you ask to any designer in gas turbine, they will tell you these features are very little. In case the coolant is not covering this thing cooling, like you increase a lot the heat transfer. So at the end of the day, it can be risky for the turbine. So what we did, we apply what is called a defissuring. So we remove small features, and after I did a very interesting mathematical operation. So by end, I cut like everything was coming after the coolant hole, okay? And obtained this kind of strange geometry here. Then after, I will compare with other geometries we are going to show like in this presentation. So, but to be honest, like the fissuring was automatic, the cut was done by hand by myself. So like it's not really like any strange mathematical operation. If you want to see the trend with turbulence, because some people say, oh, Francesco, what is happening in terms of turbulence? Well, if you increase the turbulence like from laminar to like high turbulence condition, you will see that like at the end of the day, the adiabatic effectiveness will flat out, okay? But to be honest with you, like a lot of control of hidden vortex on this structure is driven by what is called a potential flow effect. There are a lot of old studies showing that, even if I will not going to show you this kind of results today. So the question I was asking myself, I was asking several questions. First of all, like, why do we need to start from a shaped hole? Why do I need to start from an optimal geometry? Well, this is not mandatory. So I can start, for example, from a wide domain. So here on the left, you have like the original shaped hole, and instead I decide to use like if you want a bigger domain. But also I say like not only to extend like the geometry around the hole, but I decided to extend also like the exit of the coolant hole, just to be sure that this is like you have enough room. And also like I say, okay, that's fine. Instead of, I know that before I say I don't use symmetry, in this case, say let's use symmetry, at least I save the computational time. Just to give you an idea, this exercise can take about, to optimize a single geometry, let's say like about 20 minutes. this to get an answer. Depends, of course, like the mesh, residuals, and so on. But like at the end of the day, it is a good number. And we need a new optimization strategy. So like as I mentioned before, this was not one of my best ideas ever. So I say, okay, instead of starting like from an optimal solution, I start, as I mentioned, from a new geometry. I change my objective. Instead of maximize the heat transfer, I want to minimize the temperature over a volume 0.2 D from the surface and minimize pressure losses. First of all, I didn't allow to optimize all possible area, but just over the coolant until the downstream edge and also like inside the coolant channel. And where I minimize the temperature on this kind of area here that is blue. Okay, so downstream, like the coolant hole, as designers usually do. Why I didn't optimize only on the surface, but extending to 0.2 D? Mainly because I thought in this way it was a little bit more reliable as kind of solution. Okay, you don't minimize only the surface, but also like a little bit over it. So the geometry will be more resilient against any possible variation. So depending on the weights, I can get more or less any geometry that I like. If you see like on the left is more or less is a single shaped hole geometry with this kind of more complex geometries. On the right, you see what is called a branching. So at the end of the day, like what the code was doing, like it was just not showing one single channel, but was branching like in different channels, and it changed like not only in this case is 2, but we got also solution with 3 channels and so on. On the top, you have a strange geometry because you have like this kind of trench cavity shapes on the front that has this kind of sinusoidal shape. This was done automatically by the code. You have also like a downstream edge that is generated by the code. At the same time, you have this kind of a pocket where you like accumulate like coolant, like a material that has not been presented like in literature before. So this is like was a quite cool designs. And after we say, okay, let's start also like evaluating the performance. So we took this geometry, so the baseline, the strange one with the 3 coolant holes and these 2 that we did, and we compare all these 3 geometries on exactly the same mesh with exactly the same boundary conditions. So we say, okay, let's test it and see what is happening. First of all, we use like with 0 turbulence. So like in this case, I'm showing the adiabatic effectiveness. Where is blue is good. Okay, so you see the baseline, this is already an optimal, so it's already like a state-of-the-art optimal solution. What you have today in gas turbines, this is rocket science, so it's very good. So the bottom one with 0 turbulence like is already better than the original geometry, so this is pretty nice. And also like the other 2 as well, they're very good. And to be honest, like the last one, the bottom one, seems the most perfect solution because the coolant stay really attached for very, very long time in your like geometry. This is pretty impressive by any standard. If you see like with 0% turbulence, that is not realistic in a gas turbine, as everybody knows, like usually turbulence can be very high, but we want to see anyhow, because to see like what is going to be the behavior. This is like a percentage of adiabatic effectiveness gain against the already optimal solution you find already in gas turbines. And the winner is like the top geometry, where like the gain is incredible high compared to nowadays design. Okay, the second winner like is the 3-hole geometry, and the last one is this kind of strange geometry here. But what is happening when you increase the turbulence to something that is becoming a little bit more realistic, more similar to what people do usually like in experimental tests. So then maybe real gas turbines are a little bit higher, but it's still like a pretty good. So you see that you have the symmetry condition on both sides, and you see that the 3-hole is still good, maybe a little bit not so good as before, but still like outperforming. Like the third geometry, like it still show like some hot areas due to the fact that you have hot gas entering, and the last one is still the winner, even from this picture point of view. The uniform distribution is striking. So in this case, we do like the performance advantage using 3.6 turbulence. You will see that like the top one is the winner, like in terms of adiabatic effectiveness, laterally averaged. After you get the second geometry, but I don't like the fact that after like about 10 diameter, 15 diameter, like it's not going very well. The last one shows some advantage when you're far away, like from the coolant hole. However, like consider that when you are so far away from the coolant hole, if this is critical, usually you have another row of coolant holes. So like maybe it's not like something that is very useful from design point of view. But anyhow, you have like a lot of solutions. So not only a solution, you can build even more than that. And depending what you're trying to achieve, you can get a different performance. Concluding, so Toffee managed to discover by itself a new and explore idea for thin cooling. This was never shown before. Some of the solutions that we found already been proposed in literature, like the 3 holes, but the code didn't know that exist. And you can see that this geometry can be seen as evolution of trench, double steps, ramp design. And for performance improvement, like starting from an empty domain, is the best possible option as performance. If you need any question, please feel free to contact us. We are more than happy to give you any possible answer that you want. Thanks so much for your time.